welcome back. We're going to look at 322 coin change. You're given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of coins, return -1. You may assume that you have an infinite number of each coin. Alright, so let's look at some of the examples here. Coins is 1, 2, 5. Let's zoom in here. And amount is 11. Okay, so you'd imagine that if you did a 5 plus a 5 plus a 1, you'd get to 11, right? And how did we think through that problem? Well, I just took the largest number and, did a 5 here, added another largest number, and it was an 11 here, and then I took the largest number, sorry, that would be a 10, and I took the largest number that I could, and that would be an 11. Okay, so this worked in my head, this worked in this situation, but it may not work in every situation. Imagine if this was changed a little bit. Instead of a 2, 3, instead of a 1, 2 here, because 1 is such a small number, we had something like 8, 8, 6, and I don't know, 3, where I should have been taking these two instead of the largest number, right? So if the target was 9, let's say, then I took the 8, and then I have nothing to add it to, and I can't get to 9, right? I have nothing to do to get to 9. I should have took a 6, I should have took a 3, added those together and get a 9. Okay, so it seems like this is a problem that can be solved possibly as a set of smaller problems, and that would make me think that this is potentially a dynamic programming type solution, right? So let's say 11 here is some location, and I want to be able to know, like, what is the smallest number of coins it takes to get to 11? Well, it could be helpful if I knew the smallest number of coins it took to get to 10, or 9, or 8, or 7, or 6, or 5, or 4, or 3, or 2, or 1, right? And these problems, if I solve one, I could solve, all the way down. If I solve one, I solve 2, and then 3, 4, 5, 6, 7, 8, 9, 10. By the time I solve 11, I have the answer to this problem, right? And this is a possible approach. So let's think through how we would solve it in this approach, right? So how many coins does it take to sum up to 1? And how would I figure that out? Well, I have choices here. I have coins 1, 2, and 5, right? So if I already have a coin that matches it, well, then it's just that one coin, right? It takes one coin to sum up to a number that I already have a coin for, right? So how many coins does it take to sum up to 2? It's actually the same exact situation. We have a coin where there's 2, right? So it's 1. How many coins does it take to sum up to 3? Well, this one's a little harder, right? So for these coins that I have here, I don't have a 3. I have a 1, I have a 2, and I have a 5. So I can't use a 5. It's already larger, so I'm going to delete that as an option. But the coins that are smaller, I have a 1 and a 2. Well, how many? Let's say I'm using the 1. If I use the 1 and I look back to the 2, well, 2 plus 1 is 3, and it took 1 coin to get to a 2. So a potential one is this 1 coin plus using the coin 1, right? So it would be, let's say, 2 plus 1 equals 3, and that's 2 coins. And then if I wanted to use a 2, I could look back, and there's a 1 here, a 1 plus 2, and that is, that's also 2 coins. So the minimum number it takes for me to get to a sum 3 is the choices of these, and that's 2 coins, right? Okay, so what about 4? So 4, I can do the same thing. The 1, where I look back, right? And 3, it took 2 coins to get to 3, and then 3 plus 1 would equal 4. And then the 2, if I look back 2, there's a 2 here. 2 plus 2 also equals 4, right? This one took 2 plus 1 coins, and this one took 1 plus 1 coin. So it only takes, as a minimum, 2 coins to get to 4, right? I use 2 2s, and I get to 4. When I'm looking at 5, I'm in that same situation where I found a coin that matches, so it's a 1. Okay, so what are some rules, right? So rules are, if the coin exists, then it's a 1, right? So in these cases, it's a 1. And that's really the only time that that rule can apply, is if the coin exists, it's a 1, right? And then what about the other rules? So for all other coins, I can calculate, so that value minus the coin, and if that value minus the coin has some, has some type of value, so here it's, like when I was looking at, let's say I'm looking at 5, I'm looking at coin 2 goes back 2, right? So I can calculate that value minus the coin, and then what I get is, so what I get here would be number of coins to make that sum, right? And it's quite possible that that's none. And if that's none, well then, I'm out of luck. I can't do anything. Okay, so for all other coins, I can look back and make the. So what's the runtime of this, right? I have to do O of n, where n is 11 here, and then for each one of these, I have to do multiplying by the number of coins that I have, right? And let's call that m. So it's the length of the list times the number of coins that I have. And that's not bad. Can I make this linear? Can I make this linear? I don't know if I can make this linear. What would be the brute force version of this? The brute force version of this is to use the number of coins that I have, 1, 2, 5 here, and then for every one, propagate 1, 2, 5, and for every one, propagate 1, 2, 5. Even here, propagate 1, 2, 5, until we get to the sum, right? And then we count it. So here, this would be of sum 3, here would be of sum 5, here would be of sum 11, here would be of sum 3, here would be of sum 4, here would be of sum, and then we can keep on going, right? So this would be the other way, and this would be, I believe, coins, if that's m, to the power of, however many coins it takes to go down. So in the worst case, if these were all ones, I guess it would be to the power of n. Right, so if coins is 3, if there's 3 coins, and it's 11, I guess the worst case would be something on the order of this, right? But it would be exponential to the m. Okay, so I guess we're beating the brute force version. with this dynamic programming thing that we have with this n times m. Okay. So how would we think through the code? The code would be something like maybe it starts all at 0, and we multiply it by m, and that would be coins to sum would be this, and then for I in coins to sum, if I in coins, right, then coins to sum at I equals 1, right? This rule right here. And then I guess this would be the second rule, where, you know, else for coin in coins, let's say smallest equals I'm not sure yet. So for coin in coins, we want to do a look back, right? So the look back position I would be I minus the coin value, right? That would be the position. So for 5, if we're looking at coin 2, we want to look back to coin position 3. So it'd be 5 minus 2 equals 3. That would be the position. I want to look at that value there, right? So the look back value equals coins to sum, and then the look back I, right? So what if the look back value is 0? So what if, let's just think through that problem. If we had this number, the only coins that we had was, let's say we only had the coin 11, right? So if you're doing this and you only have the coin 11 to choose from, well, the coin 11 is larger than 1, so you actually can't do anything. So let's put that as an else if oh wait, no, it's not an else if. It would be here. So for coin and coins, if the coin is larger than I, then we want to continue, right? Else we're going to get this look back. Okay. Don't need that anymore. So else we're going to get this look back. Let's say we're at the 5. The coin is 2. The look back index would be 3. And then the look back here. So let's say we also had a coin that wasn't 11. Let's say we had a coin that was like 7, right? And we're at and these all start at 0. Right, but we're at the 8. We're at the 8 and we subtract 7. So 7 minus 8 would be here. Right, so the look back would be 8 minus 7 would be 1. And then the value here would be 0. So the look back value is 0. Then we actually can't do anything. There's nothing that would help us sum to here. So this would, you know, this 7 would be 1. But there's nothing that would help us sum from here, so then this would have to, you know, stay 0 basically. Right, so if the look back value is 0, that stays 0. But let's say if the look back value is not 0, then we're going to change it, right? So coins to sum. At that look back index, no, change the sum at I. Would equal the look back value plus 1. All right, so let's pull this up. Okay, so let's look at the code here. Let's move the code to the side. Let's try to size this some usable way. And let's think through what we're doing. All right, so we have coins to sum here, right? And that's going to be this, it's going to start off as this array where everything is of length. Everything is 0, right? And let's just look at what that looks like, right? So coins to sum is going to be if this is 11, it should start off as 11. Okay, so it's 11 zeros, right, in this array. Perfect. Okay, so we want to iterate through this, right? So for I in range of this amount, right, we want to iterate in some way, right? And the way that we're going to think about it is that the coins currently is a list. Let's go ahead and put the coins in a set to make it easier. Right, so if the coins are in the set, if I in coins set, well then we know that for this I, it could be 1, because we only need 1 coin to sum to it, right? So is that going to happen here? I don't think so. What do we want to return? We want to return coins to sum at the amount, right? So we can have a starting one and an ending one. Let's just see what happens. Int object is not subscriptable, right? So here I overrode it, which is bad. I want something like this. And the list is out of range. Of course it's out of range because if I'm doing this, right, so let's say amount is 3. Well, this is going to create 3 a 3-item list, right? And that list is going to look like let's see if I have this here. Amount is 11. Anyway, so if amount is 3, I'm going to create a 3-item list, and then the indices are going to be 0, 1, 2, and there's not going to be a 3. So I'm just going to go ahead and add a 1 here. And what we want to do is, instead of going to the range of this, let's just enumerate over coins to sum. I is still I. Coins will be the value. And it should be able to return amount. Okay, great. So you can see here that if this is 1, 2, 3, 4, okay, so 1, 2, 5, right? Now it all starts at 0. And then at index 1, there's a 1. At index 2, it's a 2. And then 3, 4, 5. At index 5, it's a 1. 6, 7, 8, 9, 10, 11. All right, so there's 11 items here. All right, so this is perfectly what we want in terms of setting up the length of this. Okay, and we're just going to code exactly what we drew here that's based on that diagram. All right, so for coins here, if it's in the set, we're done. Else, we're going to iterate through every coin. All right, so for coin in coins, if the coin is actually larger than I, well then we don't need to do anything because we're not going to be able to, right? I guess we don't need the else because we're continuing, but yeah, we're not going to need it. Now we're going to look back, right? And what's our look back? It's I minus the value of this coin. I don't know why I keep typing coin. It's going to be the value of the coin, right? So let's go back to our example here. If we're at, if I is 5, right? So here, the indice would be 0, 1, 2, 3, 4. Oh, okay. So great thing I'm writing this out. So it's 0, 1, 2, 3, 4. I needed a 5 here. So let me just shift everything over. I guess I really don't need something of index 0, but whatever. So I'm at the 5, right? So if I equals 5 here, and the coin is equal to, let's say, 2, then I'm going to look back, and it should be I minus the coin, 3, and 3 is going to be the indice here, right? It's going to be the index. So the look back index is going to be I minus the coin, and then the look back value is going to be that position, right? So coins to sum at this look back index, right? So that value is going to be very useful for me. So if the value here plus 1, right, is smaller than what I have currently, right? Oh wait, so I have it currently set as 0. Let's think through that. Right. So if this is 0, if the look back value, let's just finish this part. If the look back value is 0, then we can't do anything, right? Like we can't actually add to this sum. So if the look back value is 0, we can't do anything. If the look back value is not 0, then we can add to the sum. So if the look back value is not 0, then the coins to sum at I should now be equal to the look back value plus 1, or it's quite possible that there's something already in this coins to sum position, right? So let's think through that. Imagine if you had coins, 1, imagine if you had coins 2, 3, and 5, right? These are your coins. And you have 0, 1, 2, 3, 4, 5. This is your list, and you've started them all at 0, right? Now you get to 1 and 3, and you set those to 1, right? You get to 5, you set those to 1. Okay, this is a terrible example. But let's say the target is let's say the target is actually no. Well, it's never going to be more than 1. So you don't have to do a min. Actually, no, it could totally be more than one, right? So like 2 and 3. No, it's never going to be more than one. Oh yeah, you know what? It could be. So let's say the amount was 6, right? This is the amount. The target is 6. Well, with 6, you can either take it from here, right? 5 plus 1. You can take it from 4 plus 2, or you could take it from 3 plus 3, right? So 5 plus 1, 4 plus 2, 3 plus 3, you want to take the minimum value of all these valid scores, right? So basically, you have choices, right? So you have choices. Let's say that's an empty list. You have these coins here. If this is not valid, then the choices here is appended by this lookback values thing here. And as long as there's anything in your choices, then what you want to do is you want to set coins to sum at this I to the minimum value of these choices, plus 1. Let's make sure the syntax is right, and then let's just check some of the code. Okay, int object is not iterable. This should be a list of ints. Oh, I overwrote it. Okay, coins to sum is this range, right? And then maybe I can print this as well. Right, so this range of length, and it should be amounts, right? 4 of length 4, because it goes from 0 to that number. And then we want to iterate over these coins here, and if the coin exists in the set, we're going to set it to 1. Else we're going to get these choices here, right? The choices will be if the coin is maybe it'd be less confusing if I did this. If the coins is smaller than I, then I'm going to get this value. Right, so let's say coin found. Checking coin. LBI, LBVal. Okay, so coin found, there's a 2. There's a coin 2 here. And here I'm checking coin 2. And, just go ahead and print coins to sum here. Okay, so 0, 1, 2. It took 1 coin to get to 2. Here, the look back is 1. Not sure why it's 1. Okay, so I'm processing 0. And then I'm processing 1. I'm processing 2. Coin found is 2. So I'm processing index 3. Right? And I'm checking. So index 3, I'm going through all the coins. And I'm finding 1 coin that's less than 3, which is 2. So I'm checking coin 2. And the look back index of that is going to be 1 because 3 minus 2 is 1. Now, is that correct? Yeah, it's correct. And then the value is 0. But if it's not, there's only choices if it's not 0. So there's no choice here. So if the length of choices is here, so that actually remains. That actually remains as 1. So I never process 4, huh? Why don't I ever process 4? This is the length of 4. Oh, because I don't need to process 4. So the amount is 3. And the output is, oh, right. So, not to be confusing, coins to sum is, so I should return coins to sum, but only if it's not 0, right? So maybe I can just do this. I don't understand this, the edge case. So amount equals 0, return 0. It's a weird one. Okay. I don't like that edge case. This is 0 edge case. Okay, great. So we did pretty well. Runtime here would be, what we drew before. The runtime is O of n times m. And it should be pretty clear from what we talked about what that entails. We have to go through every number from 0 to amount, and then for that we have to go through every coin. It may be easier if the coins were sorted. So, here I'm going through every coin. If they were sorted, then by the time the coin is larger than I, then I can just break out of the loop, right? Doesn't say coins are sorted here. But if they were sorted, I can do that. I mean, I could also just sort it. So coins equals sorted coins. And then when I'm doing this for coins and coins, you know, if I is larger than the coin, then I can break, or I can yeah, I could break out of the for loop. And then this would be like this. Why do I keep spelling the word coint? It's not even a word. Oh, you know what? I'm doing this wrong. So if the coin is larger than I, then I can break. Because that means all future coins will be larger than I. All right. So micro optimization. I don't even know if it does anything. It might even be slower if sorting the coins is slow, because now you've added a m of log m operation. But well, this one's 498, and my last one was what? What's going on here? Why is everything hidden now? 498, 5, 14. And then previous times I tried this, I did not use dynamic programming. All right. So thanks for staying on extra. Hope you had some enjoyment watching me struggle here. I'll see you next time.